Hello.
Hello.
Any doubt from last class, Harsh?
No, sir.
We had completed up to Newton's law of cooling.
Yes, sir.
The last part of this chapter is Wayne's displacement law. Do you know about photon?
It's a positively charged particle, right?
Photon, not about proton.
Oh, no, no, sir.
You must have learned about it in chemistry.
I don't remember, sir.
These are energy packet of light. So it will have energy E is equals to hc by lambda or simply h times nu, where h is Planck's constant, c is speed of light, and lambda is its wavelength. Is it clear?
Yes, sir.
Now from this part we can say energy of this particular photon is inversely proportional to its wavelength.
Yes, sir.
So greater the energy of photon, it will have smaller wavelength. Now suppose you have a rod which is placed over any flame to heat up. So on heating, in which color it will radiate initially?
On heating, red.
Red. And further increasing temperature,
Further,
will the
it
color
will, sir, like, it will kind of be like orange and something.
good, good. Suppose in Vibgyor, violet, indigo, blue, green, yellow, orange, and red. Which radiation has maximum wavelength?
So can I repeat? Like, I was like unable to hear.
Which radiation has maximum wavelength?
Maximum wavelength out of Vibgyor.
Yeah,
Out of Vibgyor, maximum red.
good.
No, blue. Sorry, blue.
Red is correct.
Red is correct, right? Blue
Yeah.
is shorter, so it spreads in the sky. Yes, red.
So according to this relation, we can say red wavelength photon will have least energy and violet wavelength of photon will have maximum energy. According to this relation, we can say. Is it clear?
Yes, sir.
In last class, I defined you every hot body or energy of hot body will depend upon their energy, their temperature. So greater the temperature of body, it will be more hotter, or say it will have more thermal energy with it.
Yes, sir.
Is it clear?
Yes, sir.
So we can say energy and temperature will be directly proportional to each other. But in this case, energy and wavelength is inversely proportional to each other. Is it clear?
Yes, sir.
So a hot body, if it emits any particular radiation, so the maximum wavelength of emitted radiation will be always inversely proportional to their absolute temperature. It means greater the temperature of body, it will radiate more amount of energy of photon, and
Yes,
more
sir.
energetic photon will have least wavelength. That's why wavelength and temperature of body will be inversely proportional to each other. Is it clear?
Sir.
Harsh, is it clear?
Yes, sir.
So from this part, we can say the maximum wavelength of radiation emitted by hot body is inversely proportional to their absolute temperature. That is, lambda maximum and temperature is inversely proportional. So product of these two terms will be constant B, which is equals to 2.3 into 10 to the power minus 3 meter Kelvin. This B is called Wien's displacement constant. Now let me define you graph related to this part. Suppose this is lambda versus temperature. So at any instant, let's say graph is like this. For some different temperature, let's say graph is like this. So the maximum wavelength of radiation is this, and some temperature, this one. On increasing temperature, wavelength of maximum wavelength of radiation in the spectrum decreases. Is it clear?
Yes, sir.
So let's say this is T1, so lambda maximum will be at this point. This is T2, so lambda maximum will be to this point.
Yes, sir.
Just write it down.
Okay, sir. Done, sir.
Okay. Now let me give you a question related to this part. If 3 stars P, Q, R radiating maximum wavelength in blue, red, and green respectively. Arrange temperature of their surface in ascending order. We have 3 different stars P, Q, R, which is radiating maximum wavelength of radiation in blue color, red color, and green color. Is it clear?
Yes, sir.
Now, on the basis of these colors, we have to define their temperature and arrange their temperature in ascending order. So how to solve? Just write Vibgyor, violet, indigo, blue, green, yellow, orange, and red. Star P, which is in blue color. So this will be temperature of P. Star Q is in red color. So this will be TQ. And star R is in green color. So this will be R. Greater the wavelength, it will have lesser temperature.
Lesser temperature.
So temperature will be arranged like this. So if you have to arrange in ascending order, so you will say temperature of Q, temperature of R, and then temperature of P. Is it clear?
Yes, sir.
Just write it down.
Yes, sir. Done, sir.
Okay. So this is all about this entire chapter, that is thermal properties of matter. Okay.
Yes, sir.
Next we start with thermodynamics. Thermodynamics simply means, or simply it consists of two words, therm and dynamics. Therm means heat
Heat.
and dynamics means flow.
Flow.
So we can say the study of flow of heat and its various conversion into some other form of energy like mechanical energy and electric energy. This entire thing is termed in thermodynamics. Is it clear?
Yes.
So we can say this is the study of flow of heat and its conversion into other form of energy such as mechanical energy, electrical energy, and so on. Now, to start this particular chapter, let me define you some basic term related to this part. First is called thermodynamical variable. There are some physical quantity such as pressure, volume, temperature, number of mole, which may define condition of gas at any instant. So those different physical quantity are termed as thermodynamical variable. Or you can say the quantity on which the condition of gas may depend upon. The physical quantity on which condition of gas may depend upon is called thermodynamical variable. Now we have to somehow relate some different thermodynamical variable such as number of moles, pressure, volume, temperature to define condition of gas at any instant. So it is called equation of state. Harsh, do you know what do you mean by equation of state?
Equation of state.
Yeah.
So
It is
1
a
minute. Sir. 1 minute. So
okay.
Yes, I know. 1 minute. So I can't remember it. I know I've studied this 1 minute.
Okay. Equation of state is simply a relationship between these different thermodynamical variables to define the process or condition of gas at any instant. Is it clear?
Yes, sir.
So we can say a relationship between
These variables.
thermodynamical variable to define state of gas
Yes, at any age.
at any instant. In general, we have Pv to the power x is equals to some constant. We may transform this particular relation as P to the power 1 by x, V is equals to constant. Or for ideal gas equation, it will be PV is equals to nRT.
nRT.
Is it clear?
Yes, sir.
First, write it down to this part.
Done, sir.
Now, on the basis of this equation of state, we may define another term, that is molar specific heat capacity or constant. I'd also defined this particular part in last chapter. It is the amount of heat is required to raise the temperature of 1 mole gas by 1 degree Celsius or 1
Or
Kelvin
1 kilocalorie.
at given condition. It may have different value for different process of gas. So let me define you a generalized formula. First, you may write dq is equals to number of moles times C into dt. So from this part, C will be equals to amount of heat required per unit number of mole to change its temperature by 1 degree Celsius. In general, C will be equals to R divided by gamma minus 1 minus R divided by X minus 1. In this part, R is universal gas constant, which is equals to 8.314. You may write it as 25 by 3 joule per Kelvin per mole. Next, gamma. I'm defining what you mean by gamma in this part. To define this, let me give you a concept. Of degree of freedom. Do you have any idea what you mean by degree of freedom? You must have learned about it in kinetic theory of gas. Harsh?
Yes, sir. Yes, sir. It is the number of it is the number of coordinates recording of specific location. Some degree of freedom, right? Except it's sir, in my notebook it's like it's given like it is the number of coordinates required to given a specific location for a molecule and so its position.
No. Let me define its physical interpretation. Suppose you have any monatomic gas like this. So in how many direction it may contain energy? So you'll say it will have translational motion along x-axis, y-axis, or z-axis. Let's say this is x-axis, y-axis, and z-axis. So this particular monatomic particle will tend to move along this coordinate, this direction, this direction. And these all three different motion will be due to its translational part. Is it clear?
Yes, sir.
So we can say this monatomic particle may contain energy in these three different directions. So the direction or coordinate along which a gaseous molecule or particle may contain energy is called degree of freedom. Is it clear?
Yes, sir.
So in this part, total number of degree of freedom is 3 and all are due to its translational motion. So this is in case of monoatomic.
Monatomic.
just like helium, argon, neon, and so on. Suppose we have diatomic. It will act like this. So let's say this is y-axis, z-axis, x-axis. So this particular diatomic molecule will tend to move along this direction, as well as this direction due to its translational part. So we can say total number of degree of freedom in this diatomic molecule due to translation will be 3. This is any diatomic particle such as hydrogen, oxygen, nitrogen, chlorine, and so on. Next, this particular gaseous molecule may contain some rotational energy. Suppose we have diatomic particle like this. So if I'm seeing along y-axis, so it will tend to move along this coordinate, rotation possible. If I'm seeing this particular molecule from z-axis, so there will be rotation possible towards this. But if you are seeing along x-axis, it will act like this. So there will be no rotation possible towards this direction. Is it clear?
Yes, sir.
So we can say this particle will have rotational motion along this axis and this axis, but there will be no rotation possible towards x-axis. So it will have only 2 rotational part. So how many total degree of freedom in this part?
2.
3 due to rotational, translational, and 2 rotational. So in total, it will have 5 degree of freedom.
Yes.
And we are just calculating for one particle or one molecule.
So one molecule.
One molecule of that particular substance.
Yes.
Suppose if you have to calculate for triatomic for any bend shape, just like water. So shape of water will be like this due to lone pair present on oxygen. Now, in this part, let's say this is one of the axis. This is another one. This is another one. This is x-axis, y-axis, and z-axis. So we can say this particle will have translational motion along these 3 different coordinate axes, and also it will have a rotational motion along this axis, as well as along this axis. So if you have to calculate total degree of freedom in this part, so 3 translational motion and 3 rotational motion. This is we are calculating for triatomic, which is bend shape, just like water. Any doubt?
No, sir.
So we may define this degree of freedom as
6.
All the coordinate or direction in which gaseous particle or molecule may contain energy. So there will be questions related to this part. On what factor degree of freedom of molecule may depend upon? So just see, in first part, we have monatomic. So number of particles in this case is just 1. In second part, we have 2 different particles for diatomic.
Yes, sir.
So degree of freedom becomes 5.
5.
Now for triatomic, degree of freedom is 6.
6.
So first we can say on increasing the number of particles in molecule, degree of freedom may also increase. So first we can say it will depend upon number of particles in one molecule. Next, it may further also depend upon their geometry. Suppose if you have triatomic particle such as carbon dioxide. Do you know the shape of this CO2?
So CO2.
Yeah.
It's a square planar.
It will be like this.
Yes, sir.
Linear.
Yeah, linear, square planar. Yeah.
So linear shape will have same degree of freedom as that of diatomic. It will have 3 translational and only 2 rotational possible. Still, it is triatomic, but still it have only 5 degree of freedom equivalent to diatomic. So we can say degree of freedom may also depend upon geometry of that particular molecule. We have triatomic water molecule and we have triatomic carbon dioxide. But water molecule have 6 degree of freedom, but carbon dioxide have only 5 degree of freedom. So we can say it mainly also depends upon geometry or configuration of these particles. Is it clear?
Yes, sir.
Further, what will happen if you increase or decrease the temperature of these molecules? Except monoatomic, since there is no any bond with some other particle, such as diatomic, triatomic. If you increase the temperature, the bond in between them would get weakened. So they will act like spring. So additionally, it will have some vibrational energy like this. So in this case, total degree of freedom will be 3 due to its translational part, 2 due to its rotational part, and also 2 due to its vibrational part.
Vibrational part.
So total degree of freedom in this case
7.
will become 7. Is it clear?
Yes, sir.
So we may define factors affecting degree of freedom. First, you will say number of particles in molecule. Second, geometry of particle, that is shape. And third, temperature. So you'll be asked how degree of freedom will be affected with a rising temperature. So you'll say on increasing temperature, bond get weakened. So vibrational energy will included. Hence, degree of freedom increases. Harsh, any doubt?
No, sir.
So on the basis of this degree of freedom, we may define gamma as specific gas ratio. So gamma is equals to Cp divided by Cv. I will define you Cp and Cv later on, and which is further equal to 1 plus 2 by F, where F is number of degree of freedom. Now, from the above part, if you put the value of degree of freedom for monoatomic, diatomic, triatomic, you will get gamma for monoatomic. 1 plus 2 by 3, that will be 5 by 3, so it will be 1.33. Gamma for diatomic, 1 plus 2 by F, F is 5 for diatomic at low temperature, so it will be 7 by 5, that will be 1.4. And gamma for triatomic, F is 6, so it will become 3 by 4 by 3, so it will 1.33. So you will say monoatomic will have maximum than diatomic and then triatomic. And it will be greater than 1, but less than 2.
2.
Only in case of one particle or one molecule we are considering.
Yes, sir.
Is it clear?
Yes, sir.
So first write it down.
So I can scroll down. Done, sir.
So this is all about this gamma and degree of freedom. Next, we may define gas. Mainly, we have two different types of gas. One is called real gas and the other is called ideal
Ideal
gas.
gas.
Do you know the basic difference between these two parts?
Yes, sir.
Just tell me.
Like ideal gas is not. It's just like imagine like it follows the rules of like Charles law, Avogadro's law.
Okay,
It can't be real.
okay. And what about real gas? Those gases which do
With
not obey those different laws regarding ideal gas.
yes, sir.
Let me give you some another definition of these two terms. Suppose you have this particle and this particle in a gas. If there is interaction between these two particles in that particular gas, if there is interaction between particle. So due to this interaction, you will say they will have some attractive force in between them. So it will have some potential energy due to that attractive force. So potential energy will be due to interaction. And this interaction is due to their attractive force. So it will be negative in value. Next, kinetic energy due to its temperature. So it will be positive. Now, if you add these two energy, you will get internal energy, which is equals to kinetic energy plus potential energy. Is it clear?
Yes, sir.
Now, suppose in a gas, if there is no interaction between particles, I'm supposing if
There is no interaction between particles.
there is no interaction between particle of gas. So potential energy in this case will be zero since
Yes,
there is
sir.
no interaction. So it will have only kinetic energy
Kinetic
due
energy.
to temperature.
Yes.
So total internal energy will be equals to kinetic energy and will only depend upon their temperature. Is it clear?
Yes, sir.
Now, you will be asked at what condition a real gas will tend to behave as ideal gas. Let me define you. Just explain if you know.
Like if it will follow all the three laws, then
Just 1 minute.
or else there is something
Suppose
else.
in a vessel, I haven't defined you any laws till now. So how can I explain about these real gas and ideal gas on the basis of those different laws? Okay,
Yes,
that's
sir.
why I'm defining some different way. Suppose if there is particle at this point, this point, this point, and this point, if you decrease the position of piston towards downward, so volume of this particular piston will increase or decrease, or vessel.
Volume of vessel will decrease, sir.
So particle separation in that case will increase or decrease.
Particle separation will decrease.
Good. So on decreasing particle separation, we will say attractive force between them will increase. Is it clear?
Yes. Yes.
So they will tend to
Attracts.
be more interacted with
Yeah.
one another, so
Yes.
we'll have more potential energy due to interaction in that case.
Yes, sir.
But suppose if you increase the piston outward, so volume of this vessel would
Will
increase,
increase.
and particle separation will also
Will
increase.
also increase. So there will
So
be no interaction between particles, as it will become ideal gas.
No.
No.
You will say there will be lesser interaction in between this particle
Yes,
in this
yes.
case.
Yes, sir.
So on increasing piston, what I'm doing, I'm just decreasing its pressure. Is it clear?
Yes, sir.
In second case, kinetic energy is depending on temperature. So further, if you increase the temperature of this particular vessel, so particle will tend to move randomly in different direction due to that thermal kinetic energy. So in that case also, interaction between them will also decrease.
Okay.
So we are somehow trying to decrease the interaction between these two gaseous particles. So from this, we can say at low pressure and high temperature, real gas will tend to behave as ideal gas. Is
At
it
low
clear?
pressure. Okay.
So from this, we may conclude
at low pressure, at high and high temperature, real gas will behave as ideal gas.
At low pressure
and high temperature,
real gas will tend to behave as ideal gas. Now, from this part, you will be asked, suppose we have three states of matter, solid, liquid, and gas. In which case do you think we'll have maximum internal energy with it?
Maximum internal energy.
Yeah.
Gas.
Why?
Is it correct?
Yeah.
It's correct. So I don't know the reason.
So is this answer the random guess?
No, sir, like I don't know, I just use common sense. Not common sense, I was like, okay, it flows freely, so it must have internal energy.
Suppose in first case we have solid, in second case we have liquid, and third case we have gas. So in first case we can say particle will be more cloud arranged.
Yes.
Like this.
Yes.
So there will be least separation in between them. So potential energy will be maximum. And since this potential energy is always in negative, so total energy will be kinetic energy plus potential energy.
So it will be kinetic energy minus potential energy.
In case of gas, there will be least interaction.
Yes.
So potential energy will be minimum. So total internal energy will be kinetic energy plus negative of potential energy. So we can say in case of solid, there will be more amount of potential energy. So on subtracting these two parts, you will get lesser value of internal energy if we are considering at same temperature of this entire system.
Okay.
All vessel is at same temperature.
Yes. Well, then I was correct.
So from this we can say internal energy of solid will be least than liquid and will be maximum for gas.
Okay, means my reason was also correct.
Okay, just write it down.
Due to separation. Done, sir.
Now, next, we may define what do you mean by system and surrounding. Any idea about these two terms?
Yes, sir.
Just explain.
Sir, surrounding is everything outside the system that is directly that has a direct effect on the system.
Okay, and what do you mean by system?
System, so a system is a assembly of large particles. No, wait. Sir, I don't remember the proper definition of systems.
Okay. Suppose in this case, we have a vessel in which an ideal gas is kept with a piston. So all we just calculate different physical parameters related to this particular gas. So we can say this gas enclosed in this particular vessel will be under observation at all time. Is it clear?
Yes, yes, sir.
So this particular gas is called system. So you will say the gas enclosed in vessel which is under observation is called system.
System.
And all the influencing factors from outside which may affect this particular system by
Is
any
surrounding.
means is called surrounding. All the factor from outside
Having direct effect
which
on system
may affect system by any means is called surrounding, and system and surrounding combinedly called universe. Is it clear?
Yes, sir.
Now we have some different types of system. Types of system. First is open system. A system which may allow exchange of both energy as well as matter with surrounding is called open system, which allows exchange of energy and matter is called open system. Second is closed system, which allows exchange of energy only.
Energy, no matter.
And third is isolated, which restricts any exchange, which restricts all different exchange. Any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Next is thermodynamical laws. first is zeroth law. It simply explains you about concept of
two systems in a
temperature.
thermal equilibrium, right?
Yes?
Sir, it's states the two system in thermal equilibrium with the third system separates are in the thermal equilibrium with each other, right?
Yeah.
Is that law, right? Yeah, okay.
Concept of temperature. Suppose you have a system like this in which we have three different systems, A, B, and C, each having different temperature initially. So there will be exchange of heat between any two thermodynamical systems. Suppose between A and C, there will be flow of heat between A and C. Similarly, between B and C, there will be exchange of energy between these two terms. Now let me define you. This particular wall is adiabatic wall.
Adiabatic wall, yes sir.
Which will restrict any exchange of heat through it. So it will restrict exchange of heat. Through it. This is diathermal wall. Which allows exchange of heat. Through this particular wall. That's why we have transfer of heat in between A and C and also between B and C. At equilibrium, when temperature of A becomes C and temperature of B become equivalent to C. So if you remove this particular middle adiabatic wall, so there will be no further exchange of heat between A and B. It means A and B will be in equilibrium, thermal equilibrium at that case. Is it clear?
Yes, sir.
So we can say for the flow of heat between any two thermodynamical system, we must need a physical quantity that is called temperature. So there should have some temperature difference between any two thermodynamical body for the flow of heat in between them. So concept of, or simply zeroth law simply defines the concept of temperature. It is the physical quantity which allows exchange of heat between any two thermodynamical system. Is it clear?
Yes, sir.
So according to this, we can say if two thermodynamical system
are in equilibrium with each
are in thermal equilibrium
with each other. Oh, sorry. The third system.
With
third system.
Individually. Then there must be
in equilibrium
with each other.
Yes, sir.
It means temperature of A equivalent to C, temperature of B equivalent to C. Therefore, A must
be equal to B.
In this part, we may define temperature is the physical quantity responsible for the exchange of heat between any two systems. temperature is the physical quantity which is responsible for exchange of heat between Is it clear, Harsh?
Yes, sir. Yes, sir.
Okay, first write it down.
Done, sir.
Next is first law. First law mainly depends upon conservation of energy. You must have learned about it in earlier class also. Suppose we have Vash, do you want to explain it?
No, sir. I don't have the definition. It's just a whole paragraph.
Okay. Suppose this is any vessel enclosing ideal gas. So if you supply heat or eject out, this will lead to two different change. First, there will be change in internal energy, or there will be change in its work done. There will be work done on this particular piston to expand it upward, or in opposite case, suppose if heat is being ejected out, there will be work done on this particular piston to compress it. So using conservation of energy, we can say energy neither be created
Nor be destroyed in a chemical reaction.
nor be destroyed. It only transforms from one form
The other.
to other. So using this, we may define on the basis of these three different physical quantity, that is heat, internal energy, and work done. The amount of heat ejected or supplied to the system can be utilized in changing internal energy and work done. That is, dq is equals to du plus dw, where dq is heat, du is internal energy, and dw is work done. Is it clear?
Yes, sir.
Now, just write it down, then I'm explaining these three different terms individually.
Answer.
Now, in this part, we have three physical quantity. One is heat, second is internal energy, and third is work done. So we may divide these three different parts on the basis of their property into two categories. One is called state function. It is the quantity or the physical quantity which may depend only on initial and final state of gas. It will be independent of path followed by that gas. Then those physical quantity are termed as state function. Is it clear?
Yes, sir.
Such as internal energy, entropy. So you'll say the physical quantity which depends upon initial and final state of gas. It is independent of path followed by gas. So on the basis of this property, we may write du is equals to n number of moles times Cv into
CV.
dt, which is also equals to n times
And
r
R.
gamma minus 1 times dt. You may write it in terms of degree of freedom as F by 2 multiplied by number of moles R into dt. You may transform nR dt as PV.
PV.
So it will be F by
PV is
2 pressure PdV, or simply P final V final minus P initial V initial. So it will be P initial V initial minus P final V final.
Sir, here NCVDT is not a constant, right?
dt is variable term, n will be constant and Cv will be constant.
Okay. Like
So depending
because
upon,
like in
yes,
school, like we studied like a constant like this one. That's what I was asking. Like same thing. And
if temperature is
NCVDT.
constant, then in this entire term will be constant.
Okay then.
But if
Okay then.
temperature is
Yeah.
variable, so it will may
Yeah, yeah,
change.
yeah, yeah. Yeah, I was getting confused. Like temperature is constant and everything is constant.
Okay. Now, from this part, we may define its sign convention. Sign convention. If temperature of system is increased, then change in internal energy will be positive. And if temperature of gas will decrease, change in internal energy will be negative.
Negative.
Now we may define a graph related to this part. This is pressure versus volume. Suppose for three different gas, one of the gas, second gas, and third one. This, and this. Starting from this point A and finally to this B. Let's say this is first process, second process, and third process. So change in internal energy in first process, change in internal energy in second process, and change in internal energy in third process. So you'll be asked how these different internal energy will be related with one another. Any idea, Harsh?
Change in internal energy related to one another.
Just check. Internal energy is state function. It means it will be depending only on initial and final point of gas. Is the
Because
initial and final point
they have the
of
same
these,
initial and final point of right.
so what would be the relation between these two different terms? Say they all should be equal to each other.
Equal. They should be equal.
Good. Suppose we have any closed path. Now, if the gas is going along this way, so what will be change in internal energy for this particular closed path? You will say 0.
0.
Since we have same initial and final point, so difference of those two terms will be 0. That's why for any closed path, change in internal energy will be 0. Any doubt?
No, sir.
Okay, just write it down to this part.
Sir, it is independent of part, like the second line.
Path followed by gas.
Okay, path, yes. So
Yes,
is that F? No, no, right? It's not F, right?
small f. It simply defines your degree of freedom.
Okay. Yes. Done, sir.
Okay. So we can say this internal energy is depending only on temperature, since the rest of the thing is constant, number of moles and molar specific heat at constant volume. Next is called path function. The physical quantity which may depend on path followed by gas, such as heat, work done. So you will say the physical quantity which depends upon path followed by gas. So in this, we have two different terms. First is heat. Heat is equals to N times C into dt, where C will be molar specific heat constant related to that process. Related to
That process.
that process in which we are calculating. N is number of moles and dt is temperature difference. So in this part, if you have to define sign convention, if heat is supplied to the system, heat supplied to system, it will be taken as positive. And if heat is being ejected out, so dq will be negative. Harsh, is it clear?
Yes, sir.
Next, work done. Work done is force times displacement, integration. Yeah, now in place of force, we may write pressure
Pressure,
multiplied by area
area,
times
dx.
this particular quantity is also called change in volume.
Change in
So it will
volume.
be P dV integration. So in terms of graph, it will define you area under pressure volume graph. Is it clear?
Yes, sir.
Now let me define you its meaning related to different process. Suppose we have ideal gas enclosed in a vessel Suppose in first part, these gases particle doing work on this piston to expand it from this volume to some new volume to this point. So in this case, you will say this is initial volume and this is final volume. So it will act like this from some point A at low volume to some point B at some high volume. And consequently, I'm just assuming pressure will also change. That's why curve will be this. So if you extend this direction of arrow, you will get a curve in clockwise direction. So this is initial volume and this is final volume. Is it clear?
Yes, sir.
In this part, we have V final is greater than V initial.
V initial.
So change in volume will be positive and hence work done will be positive in this
Positive.
case. We can say in this part, expansion of gas. Next, gaseous particles are doing work on piston to expand it. So we can say work is done by the system. Since we have assumed these gaseous particles as system of this particular vessel. Next, graph in this part is in clockwise direction. Is it clear?
Yes, sir.
Similarly, in second part, suppose work is done on the system from outside to compress it from some initial volume to some final volume to this point. So curve will be along this way from some initial point to some final point. So if you plot vertical line, it would look like anti-clockwise direction. So we may define for this part, volume final is less than volume initial. So change in volume will be negative and hence work done will be negative. In this part, we have compression of gas. Next, work is done on the system by any external agency. So we can say work is done on the system. And last, graph or curve related to this process is in anti-clockwise direction. Any doubt?
No, sir.
So area under PV curve will simply define your work done related to this process. So it will be this entire part. And also in this case, in first part, work done will be positive, but in this part, work done will be negative. Just write it down.
Done, sir.
Any doubt up to this part?
No, sir.
Okay, so these are basic terms related to this entire thermodynamics. So let's stop here for today. Next class, I will define you some problem related to this part, and then we'll start with process. Okay.